session 17th of ARM based development. In this course, in this session, we will be covering ARM term instruction. More on term mode, and then in the next section we will be talking about the term instruction in detail. So what we have covered so far is about all the ARM instructions. We have covered everything about ARM instructions so far, and you are all ready to start writing ARM assembly code to solve various problems. Okay, and get familiarized with the different instructions, how they function, and then how to use them to solve real life problems. Okay, so you are equipped now to write assembly language already. Okay, with so much of examples of every instruction that we have covered in this session. So let us now see what is the term mode and then how they help in the embedded systems. Okay, why did ARM introduce that a new state in the ARM processor? So today's discussion will be covering this topic, and we will go into the details of thumb instruction in the next session. Okay, let us see the background, why thumb state is required, and then what is it actually trying to do, and how is it helping embedded developers to use the thumb mode state of the ARM processor. Okay, so I have already drawn this picture, so I don't want to waste your time on this. So what you see, it corresponds to the whole thing, and then thumb refers to this part of your hand, correct? So they have named it to indirectly mean that the whole ARM processor is capable of this much, and thumb mode is a small part of it. Okay, this is a symbolical representation. Okay, don't think that if this ARM is 80%, only 20% of that could be accomplished in thumb mode. You don't have to interpret exactly as the picture shows. Okay, this is only a symbolical meaning, saying that how thumb mode is a subset of ARM. Okay, and all of you all are aware that without thumb, we cannot do a whole lot of things, right? So this is named appropriately. So let us see how this design philosophy has evolved and how does it help us. Okay, so basically thumb instruction set is a 16-bit instruction. If you remember, ARM was a 32-bit instruction. Okay, what do I mean by that? Every instruction is 4 byte wide, correct? 4 byte wide, and all the instructions were always starting on the 4 byte boundary, and then the ARM processor was accessing the 4 byte at a time, interpreting the instruction which are 32-bit wide. Whereas in thumb mode, it is a 16-bit wide instructions. Okay, so one instruction is just a 16-bit wide. That means only 2 bytes. Okay, so naturally the thumb instructions are organized in the memory. Okay, on 2 byte boundaries. Please remember what is 2 byte boundary and 4 byte boundaries. You must be aware now. If our starting at this 100 here, then this will be 102. The next instruction will start at 102, and then the next to that will be 104 in decimal. Okay, suppose if it is in decimal, then 106. So it will start like this. Okay, it will all be occupying 2 bytes. Okay, so in one clock, okay, that is M clock. Alright, so earlier in thumb mode we saw that it was accessing 4 bytes instructions. So when you see the pipeline, it was filling the pipeline, prefetching the instruction which are 32-bit wide, correct? Now the same pipeline exists. Okay, inside the ARM processor nothing changes. Only thing is what the with the memory what ARM is interfacing, and then how it is reading the instruction, it changes. So it starts fetching 16 bits, okay, only 2 bytes as a instruction, okay, 16 bits. So it will be moving the 16-bit instructions into the pipeline, okay. Now what happens after the decode stage I will explain, but the fetch, as far as the fetch stage is concerned, it is accessing 16 bits at a time from the memory, which are 2 byte wide, and those are the instructions. So it has to interpret the instruction within 2 bytes. So that means assembler should have known that okay, it is generating a 16-bit instruction or a 32-bit instruction. Accordingly, it should encode the contents into the instruction. Okay, so when we say that thumb mode code, the ARM is executing in thumb state, and then from starting from 100, suppose already at the 100 ARM instructions, instead of ARM instruction, thumb instructions are filled with. Okay, who has filled it? It is the ARM's tool chain with the programmer's input saying that from 100 address 100 thumb instructions are to be filled. So every instruction will be a 16-bit wide instructions which are filled into the memory, and then the ARM processor starts fetching 2 bytes at a time from there. Okay, so that's what I call as a 16-bit instructions, and addresses the issue of code density. So what is the reason for this thumb mode? Instead of whatever you accomplish with the 32-bit wide instruction, okay, most of the things we are accomplishing it using only 16-bit instructions. So effectively we will be saving on code density. That means amount of code that you have to write, and then amount of code size that particular thumb code occupies in the memory will be smaller compared to ARM code. Okay, understood? So this is the thumb mode. So what I am saying is thumb mode code is only 16-bit wide. So if most of the instructions of ARM are implemented with a 16-bit, of course some limitations will be there, but with a 16-bit encoding, then we will be saving on the amount of memory that is needed to save that code in the memory. So that's why code density is the advantage, one of the advantages. It may be viewed as a compressed form of a subset of ARM instruction set. Okay, understand that. Okay, I will explain you how we are compressing it, how the tool is compressing it, and how the ARM processor expands it. We will see. So thumb instructions map into ARM instructions. So what I mean by that is, though thumb instructions are 16-bit wide and they are compressed and stored in the memory, after they come into the processor in the fetch mode, it comes as a 16-bit okay instruction. It goes through a decode stage where it is decompressed, and then a equivalent 32-bit instruction is generated. Okay, every 16-bit instruction mode there is a equivalent 32-bit instruction which is generated or decompressed internally in the processor. Okay, so that is in which stage? It's in the decode stage. Then onwards the processor from this okay execute stage, whatever the processor is doing internally, the register files, everything may not know, except that the thumb bit in the CPS will be set. Okay, I will show you where when the thumb mode is there, how it is different inside the processor. So CPSR there is a particular bit which will be set. Other than that, the instruction is like a similar to ARM instruction. Okay, it it accesses all the 32-bit instruction registers, and then they do similar operations that original ARM mode was doing. So that will be performed, but with some associated limitations which we will talk about it. So what I am saying is the 16-bit instructions in the memory gets decompressed okay into a 32-bit equivalent ARM instruction, and then it is executed internally. Okay, so what is the advantage of this? So in the thumb mode, only a new entity here gets activated, which is a decompressor. Other than that, the execute mode, the logic of this as well as the inside internal registers, there is no change. They are all equal, same as what you would have seen in the ARM mode. So effectively, with a smaller modification, with a minor changes into the decode logic, we are achieving some efficiency in terms of code density. Okay, in the thumb mode. Very good. So thumb programmer's model maps onto ARM's programmer's model. What is programmer's model? You must be knowing now. It's all registers. How many registers that programmers use in in the mode, particular mode, and then what are the access restrictions? What can be accessed as a 32-bit or 16-bit or byte or word? All those things. Okay, it's a programmer's model. Whether even the NDNS is part of this. So they are all same. Okay, they remain the same. Only except that the instructions are seen as a 16-bit wide, and internally they are converted to the equivalent 32-bit ARM instructions, and then they execute it internally in the processor. Okay, very good. So implementation of thumb use dynamic decompression. What I mean by dynamic means as soon as and when the instruction gets fetched from the memory, it is decompressed. It is okay. It is not a static decompression or anything. It's as soon as it is fetched from the memory, it knows that it is currently in the thumb state. So it knows that it is fetching only 16-bit wide instruction. So it gets decompressed into equivalent 32-bit ARM instruction. So thumb is not a complete architecture. Please remember, thumb mode. If I say a processor supports thumb mode, that doesn't mean that it only can execute 16-bit instruction. That is what I am saying. It cannot exist alone. Okay. If it can execute a 16-bit instruction in thumb state, that means it actually has all that is required for a 32-bit mode of ARM. Okay. So it actually on reset it starts with the 32-bit mode and then changes over to 16-bit. So 16-bit mode is a subset of the ARM mode, and thumb mode cannot exist on its own. It has to be along with the ARM instruction set and the ARM. Okay. Internally ARM processor architecture is same. So it is an add-on. Thumb state is an add-on to the ARM instruction, ARM processor. Okay. Very good. So it is not anticipated that processor would execute thumb instructions without supporting the ARM instruction set. It is not anticipated. So if the thumb is supported, ARM instruction set is default supported. But the other way is not true. Okay, ARM instruction set may be there, but thumb may not be there. Okay, so it may execute only 32-bit instruction, but it may not have a support of ARM the thumb mode. Okay, very good. Let us go to the philosophy of this. Therefore, the thumb instruction set need to only support common application functions. What I mean by common means the most important things which are used, okay, frequently or more commonly used functions are supported in the thumb mode, because thumb mode is a subset. So suppose ARM instruction is so much, the thumb mode will be something. So there should be a choice which one to be left out and which need to be supported in thumb mode. So that is decided based on the common applications which are used. Allowing recourse to the full ARM instruction set where necessary. Recourse in the sense it comes back to ARM mode wherever necessary. For instance, all exceptions automatically enter ARM state. So as once I said, thumb mode is a subset. Okay, inside a ARM mode. So processor can decide to support something, some functions in the thumb mode, and then whenever it needs to take support of the ARM mode instruction, it jumps to the ARM mode and does something, and then goes back to thumb mode for some common functions. Okay, so one example is exception handling. So all the exceptions handling are supported only in ARM mode. I explained in the last session. So inside the thumb mode there is no exception support. But one question would be, does it mean that inside the thumb mode there won't be any exception? No. Anywhere when the processor is executing, there is a possibility of any external interrupt coming. Correct? IRQ or FIQ may come. Somebody can press a reset. Correct? When it is fetching the instruction, a prefetch abort could happen. When it is accessing some data, a data abort could happen, and then system mode, supervisor mode, all the modes are there in the thumb mode also. Please remember, when it is in thumb mode, all the other exception modes are always there based on the whether it is enabled or not in the CPSR. Okay, but when those exceptions do happen, the exception handling is done in ARM mode. Okay, so it comes out of the thumb mode, executes the exception handler, and goes back to thumb mode. That's what I mean by thumb mode not supporting the exception handling. Okay, but exceptions are always could happen in any mode. Okay, even while fetching a thumb instruction, there can be a memory fault. Even while a thumb instruction is writing some data into the memory, there could be a data abort. Okay, and while it is processor is executing in thumb mode, there could be an IRQ or there could be an FIQ. Okay, those interrupts can come. Interrupts are not going to wait for which mode it is and then interrupt the processor. It may give interrupt, and then if you have this F and I bit are there in the ARM processor, CPSR, if they are cleared, that means they are enabled, then this interrupt will be recognized, and then processor comes out of the thumb mode and then goes to the interrupt vector table and they execute the handler. Okay, that is what I say, exceptions are automatically handled in ARM mode. Thumb is fully supported by ARM development tools. So what I mean by that, ARM assembler or a compiler recognizes you have to inform them. Okay, inform the tool that okay, going forward this code I want to put generate it in thumb mode. Then it will generate 16-bit instruction. Okay, and then you can let on say that I want the ARM instructions to be generated here. So mode will change over to ARM mode. You have to make sure that when you come into this code, ARM code, mode is modified. Okay, and then it starts executing the ARM code. So the development tools, all of them support both the modes. An application can mix both ARM and thumb mode subroutines together. Okay, wherever there is a performance. Okay, to optimize the performance versus code density. Okay, so if code density is important, you go for a thumb mode. If performance is important, then you go for ARM mode. So you can choose which one you want to execute in ARM mode, which one you want to execute in thumb mode, and then tools would support it, and then you will generate the code accordingly, and then processor changes the mode and then fetches those instructions accordingly. So use of thumb instruction set can improve code density. Okay, you can relate how code density improves based on the thumb mode, because thumb mode has 16-bit wide instruction. I told you that you are trying to compress the ARM instruction into a 16-bit instruction. So effectively only 16-bit code instruction is getting fetched from the memory. So only 16-bit data whatever bus will be used, right, to fetch the instruction. So the signals driven on the 16-bit. Okay, the power delivered or power consumed would be comparatively lesser compared to driving a 32-bit wide instruction bus, right? Though there is only a single bus, there is a data bus. Either data will come into the bus or instruction will come. So in a typical ARM mode, 32-bit of instructions will be fetched, whereas in thumb mode only the 16-bit instructions are fetched. So it has to drive only a 16-bit bus. So power efficiency happens because of that. Okay. Now code density happens because it occupies less space in the memory. How does it save the cost? If you have a 16-bit memory, you can, of course, the memory cost will be less, and then the interface also can be only 16-bit bus will be there, interfacing with the ARM. Okay, so that is possible. In that case, the cost of the whole setup will be less because you are PCB bit and the power required, everything comes down, and then cost of memory also cheaper, and bus width is also less. So because of that, cost will also be less. How does it enhance the performance? Because I told you most of the functions are compressed into 16-bit instruction, but they are executed as a 32-bit instruction. So there is not much of performance wise internally. Once they are decompressed, they are behaving like another 32-bit instruction. So the performance is also relatively better by using the thumb instruction. Okay, so power saving, cost saving, code density, and then performance all at once thumb mode supports. Okay. Okay, now let me tell you how the thumb state is entered by the processor. So if you recall, there is one bit in the processor CPSR register which is meant for thumb mode. So if this is set, okay, then it is in thumb mode. Otherwise, if it is 0, it is in ARM mode. Okay, that's the only difference. So based on this mode change, we can is a very quick, quickly it can just change from one state to the other state. Okay, we can call it as state rather than mode. So we call arm state and thumb state. Okay, so maybe I am using mode also interchangeably. Maybe let me try to avoid that, because mode is always associated with the processor mode, with our system mode, supervisor mode, user mode, right? IRQ mode, FIQ mode. These are all called modes. Whereas to differentiate between a mode and the state, they call this as a thumb state, not a thumb mode. Okay, so it is not part of the mode. So let me rephrase. So always we talk about thumb state or ARM state. Okay, good. So ARM processor which support thumb instruction set can also execute the standard 32-bit ARM instruction. I told you that. So the bit 5 of the T bit correspond to that thumb state. So T is set, then the processor interprets the instruction stream as 16-bit and it executes in the thumb state. Otherwise, it's the ARM state. So how do you make out whether a particular processor core supports thumb state or not? If in the name you have a T, if you see a T, that means it supports a thumb state. Okay. So that is a. So we are learning about ARM 7T TDMI. So I explained about this later earlier. So T corresponds to the thumb state support provided by this core. Okay. Very good. Okay. Now let us see how a processor in ARM state enters a thumb state. Okay. I told you that ARM core starts up after reset executing ARM instructions. Please remember on reset. On reset, what is the value of T bit? When I say that it starts in ARM state, that means T bit will be 0. Okay. On reset, it is 0. So it starts with the ARM core. That means what? The vector table has the entry to map to to point to the reset port, right? We have to write ARM instructions here because it is going to fetch 32-bit of instructions because the processor starts off with the ARM state. Okay, so please remember that. I will start from the. Sorry, friends. There was a little bit of technical interruption in the recording. So let me start from this. Where I don't know where I actually left in this slide. So let us start from this. So ARM core starts in a on reset. After the reset, it starts in ARM instruction mode. Okay, and then later on by executing a branch and exchange instruction, it switches to thumb state. Okay, so I am explaining a typical scenario where that exchange or moving from ARM state to thumb state happen. How does it happen? Okay, assume that this is the instruction. Okay, and assume that currently the PC is executing ARM core is executing this instruction. It is in the execute state. So PC will be pointing at 108. Okay, because +8 will be the typical offset. Okay, this is 104. And why is it incrementing by 4? This is the ARM instruction. So this is 32-bit byte instruction. So from the ARM state, it is trying to change over to thumb state. Now using this instruction branch and exchange with R1, and I am assuming that R1 is having a content 1001. Please remember, in a typical scenario, any address for a ARM state should have the last 2 bits as 0 because it is a 4-byte boundary. So these two do not actually have any value, correct? Last 2 bits of any address in a 32-bit address, correct? Because it's a 4-byte boundary, so it will fetch 4 bytes at a time. So the instructions addresses can jump from 100 to 104, then 108, correct? It jumps by 4 bits, 4 bytes. So, but still there is a bit set here. Okay. So when the processor executes this instruction, what does it do? ARM processor, when it encounters a BX, X it sees, that means it is supposed to exchange with what? The PC, PC with the value in R1. So it will load whatever is the content of PC, R1 into PC. But PC has to be saved, because after the branch it is supposed to come back to the next instruction, which is 4 byte next to that. So whatever is the previous value of PC, which is supposed to be 108, it will modify it with by subtracting by 4, so that 104 is copied into the R14. Okay, with the link register. Okay, link register. It will put that address into a link register and then go to wherever R1 is pointing at. Okay, this address, right, which is in R1. Okay, so it is supposed to move to 1000. Is it supposed to move to 1000 or 1001? See, one is an indication to say that if LSB is set, the new address is where you are moving, the processor is moving to, they are all encoded in a 16-bit format. That means they are all in thumb mode. Those instructions are encoded as 16-bit instruction. Okay, we are informing the processor. Okay, by executing this instruction with the R1 having this content, this instruction is informing the processor, saying that, hey, when you go to the new address which is there in R1, okay, please interpret the instructions as 16-bit. So how will it do that? How can it do that? It will do it automatically if it can change the T bit to 1, right? If T bit is 1, then it will automatically go into thumb mode, and then whatever addresses it fetches, it will fetch as a 16-bit wide instructions. So basically this 1 is to indicate that this, when you change over to the new address, okay, you have to change the T bit also to 1. Okay, that is, we are telling the processor to do it. Okay, automatically CPSR T bit will be modified by making only the T bit change. It will not change anything else. And then copy the lower 31 bit of address. Okay, 31 bit of address, because please remember, ARM is a thumb state is a 16-bit instruction. That means only the LSB 0 or 1, it doesn't matter, right? 2 bytes, anyway it is 2-byte boundary, so only the bit 0 in the address is don't care. The rest of the 31 bit needs to be considered as an address in the thumb state. Okay, whereas in ARM state, the lower 30 bit will be considered as an address, and then the LS bit 0 and 1 will be considered as a don't care. So because it is moving from ARM state to the thumb state, it has to only consider the top 31 bits, not 30 bit or 32 bit. Top 31 bits will be considered as address, and then the LS bit will be considered as a 0. So when it is loading the value into PC, it will copy the rest of the bit except the first bit, and then the first bit is set, so it will make this T bit as 1. That's it. Then it will go on to this 100,000 and then start executing this as a thumb instruction. So that is what happens. Okay, when you change over to thumb state. This is how ARM processor moves to thumb state. Okay, I hope this is clear to you. So this is the outcome of the instruction. Okay, when this is the content of R1. So note that since the instruction crosses a branch, it flushes the instruction pipeline. Please remember, when there is a branch, the new set of instructions are fetched. So earlier BX is here in execute state R1. Some ARM instruction would have been here. So in the different stages. Now because it is a branch, it will flush these two and then refill it with the thumb instructions, which are 16-bit wide. So because T bit is set, okay, the thumb instruction which is coming into decode stage will be decompressed, and then the execution starts. So previous instruction which were fetched, which happen to be ARM instructions, they are all ignored. They are flushed out of the pipeline. So other instruction which change from ARM to thumb mode, okay, include exception returns. Why exception returns? Okay, let me explain. I told you inside ARM the thumb state is there. Whenever exception happens, it comes to ARM mode. So automatically assume that IRQ was there. Okay, as soon as IRQ interrupt is suppose FAQ is not active or it is no signal is on that, IRQ is there. So IRQ has to be serviced. Okay, no other abort or anything is pending. So IRQ has to be serviced. So processor automatically jumps to ARM state. That means it makes the T bit equal to 0, and then it jumps to ARM state, executes the ARM the IRQ handler. But you have to remember when it is doing this change, it also saves the current CPSR. Okay, current CPSR into a relevant mode SPSR. Okay, in this case IRQ SPSR is there. In the SPSR, it saves the current status of the CPSR. Now in that state, T bit would have been what? Set, because it was earlier executing a thumb instruction, so it would have been equal to 1. But it has to recognize IRQ and it jumps to IRQ handler by reading the vector table and then coming to handler. But automatically it also saves the status and then only changes this. Please remember, the CPSR is modified after saving the previous content. So the previous content with the TS1 has been saved into SPSR of the IRQ mode. Okay. Now when it comes back from the exception back into the original instruction, okay, it could be a thumb instruction or it could be ARM instruction. Assume it is both are in user mode. So if it happens to be a user mode thumb instruction, it will come to know whether it is coming back to thumb mode or ARM mode by as soon as it copies the SPSR into CPSR. If you remember, there was an instruction I told that move S with PC as a destination and then the return address is copied there, then automatically SPSR is moved into CPSR, right? This movement also happens. So as soon as the SPSR content which had a T bit as 1 moves into CPSR, the processor enters the thumb state. So from the new, wherever it has to restart from, it will start fetching a 16-bit instruction because it has already moved to thumb state. This is what I am saying, that it returns from exception. If it was earlier, before going into exception, it was in thumb mode. When it returns also, it will come back to thumb mode. Please, you should remember this. It is little involved, but you have to visualize what happens during the exception, how the CPSR getting saved into SPSR preserves the original state of the thumb state of the processor. So by restoring the SPSR into CPSR, it comes back to the previous state. It could be ARM state or thumb state, but it comes back to that state. So there is a possibility of ARM to thumb mode coming back while coming back from the exception, because if it was a thumb mode where the exception happened while the processor was in thumb state, then it comes back to thumb state automatically when the SPSR gets returned into CPSR. Okay, let us see how thumb state exit happens. Okay, so in the previous example I showed you how it enters thumb state. There should be two possibilities while entering the thumb state. One is by executing the BX instruction with some value in R1 or R2, any register, with the LSB of this register set to 1. Then it moves from ARM to thumb state. Okay, this is entry into thumb state. And one more possibility of entering into thumb state is returning from exception. That also explained. Return from exception. That also comes back to thumb state, because exception needs to be handled in ARM state. It comes to ARM state on exception, and then while going back it goes to thumb state. So entry into thumb state can happen either through proper instruction or through exception return. Now I am going to explain you how can it exit from thumb state. Now it is going out of thumb state to ARM state. So one thing is very clear. If an exception happens, of course it will exit from thumb state and then it goes to ARM state, isn't it? So that is because of exception happening. But can and you know that exception is a unprogrammed event. So how can the programmer decide to move out of the thumb state? That is called programmer deciding to exit of thumb state. That can also be done by executing a BX instruction. Okay. So in the BX instruction, suppose thumb state also supports a BX instruction. Okay, this is 16-bit wide. Okay, it is executing a BX instruction with the same, assume that some register R1. Okay, R1 happens to have the bit 0, LSB as 0. Okay, suppose, then what it will do? It will know that okay, now this happens to be 0. That means it has to come back to ARM mode. So it will, when it executes the BX instruction, it will come back to ARM mode from thumb state. Sorry, I am saying mode, thumb state. Okay, sorry, thumb state. So I should not mention mode for ARM and thumb. So thumb state to ARM state happens by doing a BX, which is happens to be a thumb state instruction, but R1 will again be made 0 or the LSB, then it will come back. Or implicit return to an ARM instruction stream. Whenever exception happens, I told you, exception also can bring the state from thumb state to ARM state. I hope this is very clear to you, because this is the crux of the material. How does the processor enter ARM state from thumb state, and then how it goes back to thumb state? So this exchange of state you should be clear about. Okay. Unfortunately, the instruction simulator that we are using doesn't support thumb state. So please, you cannot practice them writing these instructions in this lab. But since I told you that instructions are all same, so you don't have to write another set of instructions to try out all the thumb state instruction. Only thing what you should be aware of is how does the processor switch from one state to the other state. As soon as you are clear, once you are very clear about this, then you learn, you know quite a lot about the ARM, that, and then thumb state. Okay, there's nothing much to know. Only this, how you can move from one state to the other state is what is more important. Okay. So let me show you one example. Okay, a typical code. This is a pseudo instruction. If you remember, address loading. Okay, we are trying to load a address into R0. Okay, which happens to be a PC address. That means what? A code, pointing to a code. Okay, assume assembly code is written like this. Okay, you can mix a ARM code and a thumb code in the same file, no issues. Only thing is, from the instruction, okay, because you look up the instruction, it looks same. Okay, BX R0 and R5, they look the same. Okay, so the processor, the assembler, when it is generating the code, since both instructions are supported in both the state, ARM state as well as thumb state, okay, the instructions are supported in both states. So you should know by some means whether it is supposed to generate a 16-bit instruction or a 32-bit instruction for a particular mnemonics you have mentioned. So that is given by mentioning the ARM 16. So prior to this, somewhere ARM code 32 would have been written. Okay. So once you have code 32, this is the command to the assembler to say that whatever instructions you encounter after this particular command, interpret them as a 32-bit instruction. Okay, so this BX R0 will be interpreted as a 32-bit instruction. So it will generate a 32-bit wide instruction. But what is it? What are we doing here? Intro thumb is a, let me remove all the things. Into thumb is a hi friends. So what happens? This is the instruction that I am explaining you. Let me get the pen. Okay. Now let me refresh it and again start from here. So what happens is, once we have that LSB as 1 here, because that label is added with 1 and then that is loaded into R0. So RSB, the bit 0 of R0 is 1, then automatically the processor enters the thumb state, and the assembler also would have read this code 16 and then it would have generated a 16-bit instructions here. See, both should match what the assembler generates and then how the instruction flow assumes the instructions are whether it is in thumb state or arm state, both should match. Otherwise, suppose you have a 32 here and then you try to jump here, it will cause a problem because the instruction would have been encoded as either 16-bit or 32-bit based on what we mentioned here. So once we match these properly, while writing the code, then there won't be any issue because it is code 16 is there. So 16-bit instructions are here, and then the control also jumping to this location. So and then we have set this LSB bit as 1. So it goes to 16-bit mode and then executes the rest of the code as a 16-bit instructions in a thumb state. So in this case, T-bit would have been set. Okay. Now as a programmer, you are interested in jumping back to ARM state because you want to execute maybe some very very critical code which has to be a 32-bit byte so that it can run faster. So you have written it such a way that you are informing the assembler saying that hey, following this code you generate a 32-bit code. Then processor will interpret all this assembly mnemonics as a 32-bit instruction, and then when you say R5 is loaded with this address and then you will just say BX R5 without that +1, okay, without that +1, what happens? The bit 0 would have been 0, so thumb state that bit would have been cleared again. Now it will go back to ARM state. So please remember, the moving from one state to the other state is very trivial, in the sense it is not doing a whole lot of job like what some typical exceptions do. Okay, please remember, moving from one ARM user mode to some IRQ mode, it involves a lot of work. Okay, it will involve a lot of work. That means it has to go to the vector table, save the CPSR, FPSR values, as well as change the mode of the processor, and then start saving the registers if IRQ handler is doing. All those things will be there. Whereas in the state change, the registers, the original registers, whatever values are there, they are all retained as it is. Okay, I will tell you whether all the registers are visible in each state. It only part of the register set is visible, but still the contents of those registers remain the same. So you can pass on some information which you have done in the one state. Suppose R2 register is loaded with a new value something, and then you want to use it in another state. It is exactly perfectly possible. Because all the things are processor remains in the same mode when it is changing from one state to the other state. Mode change doesn't happen, only state change happens. So and that also only the one bit in T bit is changed. The rest of the things are same. Mode bit in the CPSR is same. Other whether interflag and IRQ, FIQ are enabled or not, even the CPSR contents, everything remains, the conditional flags, everything remains the same. So you can seamlessly move from one state to the other state, because if that happens to be complex, then there is no advantage of having two states and then trying to save something. So ARM designers have taken care of that. So it's an excellent thinking that when you move from one state to the other state, it only changes one bit in the CPSR, and then rest of the state information is preserved and the mode remains the same. So it is a seamless movement from one state to the other state. Okay, I hope this is very clear to you how we move from ARM to thumb state and then thumb to ARM state. Okay, very good. Let us carry on. Now I will give you this. So far I have not told you what are the registers are visible. Are they all registers visible? Are the all bank registers are visible in thumb state? We have not talked about that. So let us see. Please see, so many bank registers which you saw in ARM state, correct? They are all not there in thumb state. Okay, why? Because in the thumb state, anyway we know that exceptions are not handled in thumb state, correct? Exceptions can happen, but they are not handled. So there is no need to be the thumb state processor doesn't have to know the existence of this bank register. Anyway, when exception happens, when it enters the exception mode, it will enter the ARM mode, and those relevant bank registers will be visible to it. So in the thumb state they are not visible. Okay, even in the user mode register, not all registers are accessible by all instructions. Okay, they are there physically. Please, bank register also physically there in the processor. It's not that somebody comes and takes away, but they are not visible at all. They thumb state doesn't even know the existence of other modes. But here, so it is only the these registers are visible. Okay, core registers, and the top these registers are used only by specific instructions. Okay, and then the rest of these registers which happen to be a generic purpose also, you could use R13 or R14 or R15. Okay, in a typical ARM mode, they are all tied to a particular function here. Okay, why is it so? Because they want the in the thumb mode, sorry, thumb state, there is only a 16-bit place for encoding any information. So most of the things need to be hardwired or are assumed to be a particular function, so that it need not be configured in the instruction. So to simplify the instruction encoding, some assumptions have been made. Okay, so it always assumes that R13 is a stack pointer. Okay, in ARM state you can have anything as any other registers also as a stack pointer, whereas that is not true with the thumb state. And then also, though all the low registers are visible in thumb state, not all the high registers are visible in all the instructions. So maybe some part of the instructions in the thumb state may access them, but not all of them. Okay. Similarly, CPSR, it is whole thing is visible, but accessibility wise, it cannot change the mode of the mode bits of the thumb CPSR. In the thumb state, you can't modify the mode, because if you modify the mode, you are supposed to be aware of the mode bank registers, which is not there in the thumb state. So it will remain the same mode as what it was earlier. Okay, you cannot modify the mode of a processor in the thumb state. Okay, let us see what are the other things. Thumb instruction set as a subset, I told you already. It has a restricted view of ARM registers. Only low registers, we call it as a low, R0 to R7, and these are all hardware. It is meant for special purposes. And then mostly the stack pointer is is very important, because it always assumes that R13 is the default register to be used for in the thumb state if there are stack related operations to be performed. Okay, I will explain you what I mean by that. Okay, in the previous example so far in ARM state, we have seen that any register could be played. You could use it as a stack pointer. Okay, that if you remember that full and decrement or empty and increment, all those things, right? So here there is a restriction. Remaining high registers have a only restricted access. Okay, a few instructions allow high registers to be accessed, not all of them. And CPSR condition code flags are set by arithmetic and logical operations. Okay. One more thing I need to tell you here: the CPSR condition flags, correct? CZNB, our friends. Okay. In the ARM state, we will say move yes, add yes, right? Only when we mention yes, this state register, the condition flags are modified, right? Otherwise, they are not modified by the ARM in the ARM state when you execute this instruction. Whereas in thumb state, there is no option of mentioning yes at all. You will only say move or add. Okay. Anyway, move doesn't support, disturb the state. Arithmetic and logical operations, okay, add or and anything you do, whether you mention yes or not, they will default affect this condition flags. Okay, in the thumb state. I will tell you why. Okay, that maybe think it over. Why they have removed that yes option in the thumb state. Okay, let us have one small quiz here. Take 2 minutes break. You don't need more than that. Please read it out, and then decide the answer. Then we can continue. Okay, welcome back. If you say all the options are looking reasonable, I'm sorry, they are not actually. The correct option is C. Okay, I will tell you why other options are not making sense. There is no need for more registers in thumb mode. It is not that there is no need. Okay, as a programmer, we want as many registers as possible, right? We can't say that there is no need in our thumb mode, thumb state. Okay, I should have mentioned it as thumb state. Okay, sorry, you write it as thumb state. Okay, there is no more. Okay, so thumb state, we want all the registers, but the problem is with the 16-bit encoding possible, only 16-bit encoding, we cannot have all the registers encoded. Okay, why? Because if you allow more registers to be encoded, your number of bits required to encode them will also increase. See, when you have R0 to R7, how many bits are required to encode them? 3 bits, correct? 000 to 111. Okay. Whereas if you say, even if you want to include R8 also into it, you need a 4-bit wide encoding. And in the instruction, you need to decide in the 16-bit instruction encoding. We, as a processor designer, we have to decide whether we are going to have 3 bits for the operand, register operand, or 4 bits for register operand. If you use more bits for the operand, then naturally the amount of bits left for operations will come down. So they have to, as a designer, they need to optimize on number of bits required. So basically, what they have done is reduce the number of registers so that the number of bits required to encode them in the register in the instruction comes down. So they can compress the instruction bit. So high register increase the power. There is no relevance to high registers and low register increasing power. Okay, it doesn't make sense. Allowing access to all registers in the process will slow down the execution of thumb state. That is also not true. And this is also not true because we always want, as a programmer, we want more registers. But because of the restriction that 16 bits only are allocated for the thumb instructions, the processor designers have gone in for only reduced visibility of instruction set. Okay, very good. Now let us just quickly look at the similarities. The thumb instructions are 16 bits long. Okay, you know that, and they map into ARM instructions, so they inherit many properties of the ARM instruction set. They exactly map, one-to-one mapping is there. They are also the same like load, store, data processing, data transfer, and control flow instructions. Okay, all of them the same set of instructions. Okay, there is no change. Let me, and then it also supports all the different word widths. Okay, and then please remember the 32-bit memory is visible in the 16-bit thumb state also. So the memory what is there is still a 32-bit memory. Okay, so you don't assume that okay, once it enters the thumb state is only half of the memory is visible. No, even in thumb state the whole unsegmented 32-bit is visible. However, in order to achieve 16-bit instruction length, number of characteristics features of ARM instructions have not been supported in thumb state. Okay, some of the characteristic features are not there. That's all. But holistically they work on the 32-bit registers. They work on the same memory. Okay, 32-bit memory, all that is same. Okay, internally, because I told you that internally registers are all 32-bit. So whatever address it generates are also 32-bit. So the whole 32-bit memory is visible even in the thumb state. Okay, that you should know. And then what are the differences? Most thumb instructions are executed unconditionally except branch instructions. What I mean by unconditionally? If you remember the instruction format, the first 4 bits are conditional code, correct? So you can say add EQ, right? And then sub NE, all that we were able to do it in ARM state, but they are not possible in thumb state. Okay, their default, all these instructions are, you can mention only add and sub. If you write like this, maybe assembler may give a warning, or it may just not, or it will not allow you. Okay, because always this is executed. That means what? This conditional flag is this not a conditional flag. It is on condition in which this particular instruction needs to be executed is taken as always. That means 1110 if we call this pattern. So this particular bit pattern is not there in the 16-bit instruction bit at all. Okay. So conditional codes are not there. So conditionally you cannot execute the instruction, but instructions can affect the conditional flags, but you cannot execute the instruction conditionally. Please remember, only a few instructions may be executed like that. Similarly, the data processing instructions use two address format. What is two address format? In a typical ARM state, we will say that RD, RM, RN. Correct? So you can write, you can mention 3 registers, whereas in thumb state you can mention only 2 registers, R1, R2. So what does it mean? That means only RD, RM. That means it will assume one of the RD itself is RM. Okay, they both are same. Okay, RN is there and the RM. So only 2 register format is allowed in the thumb state. Okay, the reason being, again, there is the limited space for encoding the information. So, and the ARM, in compared to ARM instruction format, the 16-bit thumb instruction format is a little bit not very regular. That means the bit pattern will be, we are not going to look into the patterns how it is encoded, but they are not in a very regular, as a condition flag will be here, and then you have seen that, right? A specific location is reserved for RD, then something for RM and something for RN. All those fixed locations were mentioned, fixed, because there are the ARM designer had a 32-bit of instruction bit to place them, whereas in the 16-bit instruction encoding, they have to accommodate what is possible within that limitation. Okay, so a dense encoding is. There are no stated register access instruction. There is no MSR or MRS instruction which accesses the CPSR. They are not there in the thumb state. Okay, you cannot access the status. That's why I'm saying you cannot modify the code. You cannot modify the thumb state in the thumb mode. Okay, and then you can't modify the conditional facts also directly. You can execute an instruction and then get modified, but you can't write into them, because unless you have this MRS and MSR, you cannot access any of the contents of the CPSR in the instruction. Many addressing modes are not supported in thumb state. Okay, so these are the differences, and no blank registers, of course, and privileged modes in thumb state. Now the biggest register difference involves in the SP register. Okay, stack pointer. Okay, I mentioned it. That means actually push and pop are the 2 instructions which are supported in thumb state, and they default use the R13 as the base register. Okay, and they internally convert into ARM instructions with a load and store LDM or STM or LDR STR, but when you say push or pop, they assume it as R13. Okay, I will, when we talk about the instruction, I will explain more in the next section, but remember that there is a default stack operations are assumed as assumes R13 as a stack base pointer. Okay, stack pointer, and there is no swap registers in the thumb state. Again, sorry about this. It should have been thumb state. Okay, very good. So no support for co-process instruction. I have not talked about thumb state, but let us co-process instruction. I will talk about that later. And then barrel shifter operations are separate instruction. What I mean by that, if you recall, the ARM state has you can have one of the operands. You can say LH, sorry, you can say arithmetic shift left, AHL. Okay, so we can mention as a part of an instruction itself, we can mention the barrel shift operations, right? Whereas in thumb state, they are all separately given as the instruction. So you cannot, along with the instruction, you cannot mention the barrel shifter operation. Why? Again, the limitation because of the instruction weight. So, but support for barrel shifter operation is there, but you have to mention it as a separate instruction. Okay, and then all data processing instructions set conditional flag. That is one more in. No, you cannot mention S flag, because again it is one bit will be wasted if S bit needs to be mentioned. So they have removed the S bit option. That means what? Every instruction, logical or arithmetic operation, will affect the conditional flag. Okay, the CSZNV. So these are the basic differences. Now let us see how it is implemented inside the processor. A thumb instruction set can be incorporated in the 3-stage pipeline. Okay, with a minor change. Okay, whereas in a 5-stage pipeline ARM9 it is little bit trickier, but we are not going to cover that ARM9 anyway here in our course. And then biggest addition is the thumb instruction decompressor. Okay, I mentioned it earlier, but I will tell you how it is implemented. This logic translates thumb instructions into equivalent ARM instructions. Okay, since ARM does a relatively little work in phase 1 of decode cycle. Please remember, fetch cycle, decode cycle. In that phase 1 is there. Okay, there is a signal clock, and then if you two-phase signal, if you have seen, there is one more second phase. In the first phase, the decode logic, the ARM instruction does very minimal work because it is only resolving the registers and all that, and actual access of the register accesses happen in the execute stage only. So what am I trying to tell here is the decode stage can easily accommodate the decompression logic. That means I told you that a thumb instruction gets expanded to ARM instruction in the decode logic. That means it is decompressed. So this job of decompression is not delaying the decode logic so much, because you know that when the decode is happening parallelly, some memory access or some internal register operation or arithmetic will be happening, and they will be taking more time. So decode logic will not be a bottleneck in deciding the M clock for the particular processor implementation. That's what I am trying to say. So thumb pipeline operates in exactly the same way as ARM pipeline. Please remember, they work as the same way. Okay. So I told you this decompression happens here. Okay. So to come to decompress, perform the static translation. That means what? It has a 16-bit. Okay. What I mean by this is the translation is not going to modify. Okay. It will, as soon as the instruction come. Okay, 16-bit instruction. Every pattern of 16-bit instruction, the thumb state instruction, has a fixed pattern on ARM state. Okay, they convert it into 32-bit ARM state format. Okay, there is a direct one-to-one mapping. Okay, that is what I call as a static translation. Okay, so that translation happens, and this involves performing a lookup to translate. So what I will be zero extending, 3-bit registers are expanded to 4-bit register, because when it is converted into a 32-bit instruction, any register mentioned in the 16-bit instruction, maybe you have mentioned as R1, you would have mentioned it as a 001, 3-bit, whereas it comes here as a 4-bit value. So it can be zero extended, because that is the reason. Anyway, only the lower bit, lower set of register R0 to R7 are used in the most of the instruction here. So they can be zero extended without any problem. Okay, it will still map to the same register which was referred in the thumb state instruction. Okay, I hope this is clear to you. So this is what is being done by the thumb decompressor. So this is the internal operation. So based on whether it is a thumb state or ARM state, a 32-bit or instruction, 32-bit or 16-bit instruction come here, and then the pipeline interprets it as thumb state or instruction ARM state based on the T-bit, and then this is 16-bit. Okay, this is another 16-bit. Okay, so you may wonder how it is. Anyway, instructions are accessed from the memory as 16-bit only, right? 16-bit instruction, they are coming as a 16-bit. Why is a low or high is given? It could be because the memory and ARM processor, how they are interfaced, it's very flexible. You remember that there is a separate data bus, and it could be a 16-bit width or 32-bit wide data bus can be there. So the memory can be connected to the processor in so many different ways. So based on that, either the memory may give the instruction based on the whether low half word, lower half word or higher half word, those instruction may land into any of these buses. So it is internally handled by how it is connected on the memory and the processor. So you might get a instruction, 16-bit instruction always in a lower half word, or it could come the higher half word and lower half word. So based on the type of the state, it may choose one of them. Okay, or it may choose this decompressor itself will be will not be there in the normal typical ARM state. This is how, what is the width of this? It will be 32. Okay, so this will not be functional when ARM, if it is in ARM state. Suppose the T bit is 0, then ARM instruction 32 bit with the instruction comes and then it goes through this and then it goes there. Okay, decoder, it enters the decode stage. Okay, this is the pipe in a fetch stage. This is the decode stage. Okay, so let me, if suppose you have missed out something, let me explain this little bit more. Okay, so this is the internal, okay, organization of the inside the processor. Okay, so this is instruction fetch mode stage, and the whole thing is a decode stage. This is the decompressor part of the decode logic, and this is normal decoding of instruction and then identifying the register operands and all that. Now when this instruction come in, based on the T bit, it may be getting a 16-bit wide instruction or 32-bit instruction from the memory. Okay, and then they will enter the mux based on the whether how memory is providing the instructions, 16-bit instructions, whether in the high, this 2 or 16-bit, okay, bit, this 2 or 16-bit bit, and this will be a 32-bit wide. Okay, this is 32-bit. Why? This is a typical data getting read either using LDM or STM or LDR or STR. Then those instructions anyway will fetch 32-bit data. I told you that memory is a 32-bit memory, segmented memory, unsegmented memory. So 32-bit data only will be read by the processor, either it is in thumb state or ARM state. Suppose instructions only, there is a difference. So if it is thumb state, what happens? The 16-bit instruction come through either this bus or higher part of the data bus or lower part of the data bus. The instruction enters and then it gets decompressed. This logic gets activated, and then what you get out, what you get is a 32-bit instruction. Okay, either it is taken from here or taken from there based on the ARM state. Now from here onwards it behaves the same way, like whether it is a ARM state or a thumb state. Okay, from this onwards the behavior of the processor internally will be same. So every 16-bit instructions have a unique 32-bit instruction mapped to ARM state, and then onwards it acts as a ARM instruction. Okay, please remember that. So an example, suppose you have written in a thumb state, you have written an instruction like this. What it means? See, there is no conditional code. EQ or ME is not there, so it is always executed. Okay, it is always executed, and there is no S here. It is default assumed to be F. So that means it will affect the conditional flag. So S is there, so it is always assumed that S is present. And then I also said one more thing: 2 operand instead of 3 operand in thumb state, it is a 2 operand. That means what? One of the operands is same as RD. So RD is there in 2 places, and immediate operand is exactly the 8-bit is coming here. S is added because always S bit is there, and then it is executed always. That's why when it gets expanded, a 32-bit instruction is generated like this. This is the code for conditional flag always. So this instruction is always executed. Okay, S bit, where is it? It is here. Wait a minute. I think if I remember correctly, it is here. Okay, so S bit, it is set. So this instruction as such is going to impact the conditional flag, and this is to say that it is the immediate operand, because immediate operand is there. Okay, and then RD is same register is put here, and then you see here it is extended with a 0. Okay, and here also extended with a 0. Okay, what is this? It could be an add operation. So it is actually 0 100 is a data processing instruction. So it is mentioned here with the immediate operand. Okay, so add instruction is given. Okay, and the RD is written this way, and then immediate operand. One more operand is additional, third operand is the immediate operand. So you can see that any instruction in the thumb state maps to a equivalent ARM instruction. Okay, That is what you should remember. Fine. This is how it is done. And then if you recall, originally in the thumb state 12 bits are reserved for immediate constant. Now since we are only reserving 8 bit in the thumb state, the remaining will be filled with 0. Okay. So that's all. This is how it is expanded. So typical thumb system, how they are used, it should be clear that all thumb systems include some ARM code for handling initialization and extraction handling. Okay. ARM is there always. It is likely, however, that most thumb applications will make more than this minimal use of ARM code. So more of ARM code may be there. That's what I'm saying. Okay. And then a 32-bit memory or 16-bit memory could be used. So we can use a fast 32-bit memory for ARM code and then use a 16-bit memory for thumb code. Okay. See, again this is independent. It is left to the designer, system designer. So typical, which is the best way of designing it is put all the ARM code in a 32-bit memory and then put all the thumb state code in the 16-bit ROM, and then it also can be off chip ROM, so that it can be a little bit slower also. Okay. So this is how a typical example of thumb system may look like. Okay. So what are the benefits? Some numbers. Thumb code requires 70% of the space of the ARM code. Okay. Why it needs more or less? It needs only 70% of the space of the ARM code. Okay. Suppose you are doing some job, okay, in ARM state. Okay. And then you are converting the whole set of instruction into a thumb code. Okay. Thumb code. That means you are executing everything in thumb state. Now the effective code size, suppose this was occupying 16 bytes of 100 bytes of code space, it would only take 70 bytes of thumb instruction. But please remember, the number of instructions here will be more than the number of instructions here. Why? Because every instruction takes 32 bits here, whereas every instruction here takes only 16 bits. So, but still it occupies 70% of the space. So the number of instructions here will be more, okay, greater than number of instructions here in ARM state. Okay, whereas code space wise, this is less than this space. Okay, okay, maybe I will I'll write it like this. So the space wise this is less, okay, whereas number of instruction wise this will be more in ARM state. Okay, so how much space? The thumb code uses 40% more instructions. That's what I'm saying. Number of instruction wise this will be more, okay, than original ARM instruction, but space wise it will be less. So 32-bit memory, the ARM code is 40% faster. Okay, if suppose you are using a 32-bit memory, ARM will be running faster there because you are accessing 32-bit at a time. But if you are using 16-bit memory, the thumb code will be faster at a 45% faster than the ARM code. Okay, so because you are accessing it as 16-bit and this is in sync with the way the processor wants the code to be provided to it. So 16-bit is more beneficial in the thumb state compared to a 32-bit memory in an ARM state. Thumb code uses 30% less external memory power. Okay, it uses less power because it only powers half of the bus in the database. Okay, the data portion of the bus for fetching the instruction. So performance is all important. Then what you do, you can use 32-bit memory and ARM code. If cost and power are more important, 16-bit memory with the thumb code. Okay, so this is the overall comparison of how code space compared to instruction and which is better, which memory to be used in which state is what is given. This is the summary of all of them. Okay, I hope you understood the reasoning behind all of them. So we have come to the end of this session. We will touch on the instruction of thumb state in the next lecture. Okay, so today we saw the background design philosophy and how it is implemented inside the processor, the thumb state of the processor. Okay, I hope you understood everything here. Nice to talk to you, and then we'll again meet in the next session. Have a nice day. Thanks for your attention. Bye bye.